Now we are going to discuss ring complexity, convergence, and stability. So the following steps are involved in almost all modern numerical methods of solving electromagnetics problem. First, we can decompose the domain into many small subdomains that are much smaller than wavelengths, and the domain can be referred to as region, object, or something similar. A second matrix equation is derived that accounts for iteration of the subdomains. Each subdomain is usually given one or most often several unknowns. The number of subdomains represents the degree of freedom of a domain, and we often say that we have discretized a domain using numerical method. The total number of unknown n to be solved for represents the degree of freedom of the system. And the two most important measures of the efficiency of the numerical method are a memory requirement and the computational time. Ideally, both of them should be small. For example, to store the unknown in the system and the relevant matrix elements, a computer's random access memory must be used efficiently. So solving the matrix equation requires computational resources such as CPU time. The memory usage will scale as the order of n power alpha, and that will be order of, right? That's why we say or. And the CPU time will scale as the order of n power beta. And here alpha and beta are numbers larger than 1. We have just discussed the scaling properties of the memory and the computational time with respect to the unknown n. And these characteristics are known as memory complexity and computational complexity. So let me define the meaning of or from n power beta and similar expression. We say that r is in the order of n power beta when n tends to infinity. We imply that the exists a constant c, such as that r tends to c multiplied by n power beta. Again, it's under the condition that n tends to infinity. And here r is the resource usage. It can be memory or CPU time. In this case, we say that the asymptotic complexity of the algorithm is the order of n power beta. Alternatively, we simply say n power beta. So for large scale computing, where n is usually very large, the term complexity refers to asymptotic complexity. This mimicking the situation when n tends to infinity. And the complexity of an algorithm also determines the scaling properties of algorithm resource usage. So for instance, if beta is equal to 2, the resource usage quadruples every time the number of unknown n doubles. So when r refers to the CPU time, the constant c depends on the speed of the hardware and the detailed implementation of the algorithm. However, the complexity of algorithm does not depend on constant c. And one can see that here the constant c is included separately as a multiplier. So depending on the algorithm used, alpha can be as large as 2, beta can be as large as 3, and efficient numerical algorithm intends to make these numbers as small as possible. So in most cases, we don't expect to have it smaller than 1. When alpha and beta are large, the resources needed can easily swarm the largest supercomputers we have. So for instance, Gaussian elimination for inverting a matrix is of complexity n cube, and a CPU time can end up being in the order of months or even years when n is large. So it's often called the cruelty of computational complexity in computer science jargon. So recently, many previous complex and solvable problems became more accessible to scientists and engineers using moderately sized computers. It occurred due to advent of fast algorithm for reducing alpha and beta when solving this equation, as well as the leaps and bound progress in computer technology. So the latter helps to reduce the constant C. And alternatively, some researchers have designed algorithms to solve problems using a hard drive as well as RAM as a storage space. So these are usually known as out-of-core solvers. Even then, if algorithm memory and computational complexity are poor, the hard drive's memory can easily become insufficient. So we can use parallel computers to speed up solution to larger problem, but they do not reduce the computational complexity of the algorithm. So if a problem takes CPU time proportional to n power beta, then an ideal parallel algorithm to solve the same problem with P processor has CPU times that scale as this value over P. Right? Such an ideal algorithm is said to have a perfect speed up and 100% parallel efficiency. However, because of the communication cost needed to pass data between processors, the latency in computer memory access increases as problem size increases, and 100% parallel efficiency is generally not attained. So in this case, the CPU time scale as parallel efficiency sigma as a multiplier. And again, as can be seen from above, the used parallel computers do not reduce the computational complexity of the algorithm. It only helps to reduce proportionality constant in the resource formula. And traditional numerical methods are inefficient. In contrast, fast algorithm in computation electromagnetic takes the use of many of this electromagnetic analysis method. And changes are expected in the near future. So let's say we have a problem with n degrees of freedom or n unknowns, and then many of these fast algorithms use the order of n logarithm n memory. It is different from the traditional methods that require order of n square memory. And similarly, a novel fast algorithm can have it close to n or logarithm n, and this is opposed to traditional methods with n square. So when n becomes very large, there will be a tremendous discrepancy in memory and time usage between fast solvers and traditional solvers. So the researchers began developing many numerical methods to solve Maxwell's equations, starting from 1960s, and the earliest of these were a finite difference time domain method developed by Yi and the methods of moments. And a finite difference time domain method processes to solve the partial differential equation associated with Maxwell's equation directly. And in turn, the methods of moment converts Maxwell's equation into integral equations using the principle of linear superposition and Green's function. So the ability to convert Maxwell's equations to integral equation using the linearity of Maxwell's equation, which might not be the case in some media. And methods of moment evolved from hierarchical method And it's also similar to the boundary element method developed in the structure community. So many works have been developed to extend the method of moment for solving three-dimensional electromagnetics problem. And a finite element method, which was initially popular in the structure community, was soon translated to the electromagnetics community for solving problems. So many methods popular in the fluid community for solving special differential equations are also being brought into the electromagnetics community for solving Maxwell's equation.